everyone. Thanks for attending my talk on the maximum likelihood ensemble smoother with multigrid. I'm from Colorado State University. So the new concept acronamed as MLES originated from our research collaboration with Dr. Milija Zupanski from Syria at Colorado State University, Dr. Jacob Schroder from the Department of Mathematics and Statistics at the University of New Mexico, and Dr. Robert Falgout from Lawrence Livermore National Lab. Today, I will focus on describing the new concepts and share some preliminary results. I'd like to acknowledge Chris Hurst for the preliminary study. Chris is my PhD student, and he's a lead researcher in this study, and will continue the development and application of this new method. In the introduction, I will explain what is MLES multigrid. Let me clear this screen. Seems okay. In this introduction, I will explain what is MLES multigrid, what motivates the development of this concept, and then provide an overview of the main technical points. We have some very preliminary results to share and discuss. More importantly, through this investigation, we became more clear on what we should do next. So first, let's start with the cost function. This cost function is derived based on Bayes' theorem with assumption of Gaussian type errors, for example, the background errors and observation errors. The first term is like a regularization associated with the model background. While the second term measures the misfit to observations. Our goal is to minimize this cost function by adjusting the initial starting point of the control vector, Q hat. This is a control state, Q hat 0. Let's clarify some symbols first. Q hat with the superscript F is a forecast. P is the background error covariance matrix, which in our case will be obtained from the ensemble. O is the observation vector. H is our observation operator. For the data error, the R is the error covariance matrix. M is our basically nonlinear model, and you can basically have model propagates forward. And here you see we have more terms at different time points in a big time window. So this is the maximum likelihood ensemble smoother look like. So this method is built on our research working with the filter MLEF, maximum likelihood ensemble filter, which was developed by Dr. Zupanski over a decade ago. We have had a good experience with its application to computational fluid dynamics with combustion. This sketch graphically illustrates the difference, maybe a little bit exaggerated, the difference between the filter and the smoother. The filter is the blue. You can see if, let's say in this big time window, we have 5 time points, and each time point we have data available, then we at this time point, and the filter will assimilate data and then move on for the next point, sequentially continue the process. While the MLES, the smoother, will just take all the points where the data available, formulate one cost function. We optimize that, and by adjusting the initial starting condition, and then get a better or optimal state. So that's the supposedly there will be some difference between these two states. So most ensemble-based data simulation methods are sequential. That is classified as a filtering method, I believe, in the field. There are several limitations of filters that probably impact some applications adversely. One example is associated with assimilation of time-integrated observations. For example, when we do the turbulent combustion flow simulations, we have measurements at a certain location. We typically do a time averaging measure of this instantaneous reading. So this is one of the example we would like to apply one application area. The other example is that we're interested in most of the time estimating the model parameters. So this is particularly a problem for nonlinear problem. For such problems, the smoothers probably are better equipped since the prediction model is an integral part of the analysis process. Nevertheless, there are some challenges for smoothers. One is related to nonlinearity. The second challenge is due to increased cost of calculation, since the use of the prediction model can add quite a bit computation overhead for smoothers. So this motivates us to introduce the multigrid in time to the smoother. The multigrid in time, that's the second part of our approach. So I have done some literature review since that the meteorological community have already employed a spatial multigrid method with data simulation. So applying the multigrid reduction in time to data simulation is kind of interesting. Perhaps is a new aspect of it. So this process can be seen in this figure. So this is a multigrid. This is a kind of like a full multigrid, a relatively full multigrid. This ideally will start at the coarse level, and then we prolong to the finer level. So coarse level and then medium, fine, finest. So we want to start from coarse level, but sometimes it could be better if you have more computational power, and then you start from relatively decent mesh size, and then smooth your problem a little bit. That's good too. But for computational efficiency, you can if your algorithm is really robust. So you so we'll start from the courses. So we work our way up, and then if we also use I will describe this a little bit more later. Dedicate the slide to describe the process. So one thing that one piece of the motivation is this computational efficiency, and then the other piece of motivation is that we would like to take advantage of the future architecture and the trend using multigrid reduction in time, and then we can parallel our code in time. So this way we can provide a further speedups and effectively make use of this new architecture. As you can see, the architecture trend is that the clock rates become flattened, but more concurrency is added. So if we want to do more interesting larger scale calculations, particularly for scientific simulation or engineering application, we will require algorithms that parallel in time. Of course, some problems can be suited very well for parallel in time, like this optimization type of application. So basically, this is the main motivation for our work on MLS and multigrid. So to just point out the start, so just give direct comparison between these two methods, the filter and the smoother. This is so that's basically, as you can see now, we are working with the new variable psi instead of our original control variable, and this is because in general, the state of variable is the state vector is multivariate, and they can vary a few orders of magnitude. So it's not feasible to invert the forecast covariance in a high-dimensional problem. So we typically do a change of variable psi, which is dimensionless. And the cost function being solved is now in terms of psi. Specifically, this is the difference between the filter and the smoother, and this is our nonlinear numerical model, and this is where we involves example of runs during the formulating the cost function. So I'm trying to get this done. Okay, so what is involved in the MES process? This can be illustrated by this figure here. Let's say we have a time window from T0 to T5. The ensemble consists of one control run, the black, and then you have 3 members. Assume that the data available for 5 data points, 0, 1, 2, 3, 4. And now for the filter, you will optimize a cost function for the entire time window. But MEF, the filter will optimize one cost function at each time when there is a data available. So that's just the process difference here. So if we go next. So the MES process, I'm going to use a 2-grid multigrid to illustrate the process. So when you add the multigrid in time, as we said earlier, we can start by obtaining optimal state from the coarse mesh. If you assume there's only one data point, one time point, the data is available in the time window, and then you can just take, for example, in this case, you can take it from T0 to 4. So that in that case, your smoother recovers filter. So that's as a first step we would like to verify. Of course, depending on the problem, you have a coarsening ratio, how many time points you have in this time window, and what's the coarsening ratio that depends on specific problems. But the point here is that if you have one time point where the data is available, your smoother should recover the filter for this big time window. Now, if so on the coarse grid, so you achieve optimal state, and then you take the corrections, and then you update your medium level. And then on this medium level, now you have a good starting point to have optimal state from the coarsest mesh, and then you continue the process, and then you can do more work on this level before you go back to on the finest. So this is the kind of a typical W cycle. So the process is really similar to the spatial multigrid. You essentially starting from courses, hope to get a reduction of the work on the fan mesh. That's where we can get a computational efficiency. So for the present study, we explore the predictability of a simple chaotic fluid dynamics system, where a model problem with Kuramoto-Swachinsky problem. And this is basically the first derivative, the second derivative, first derivative in space. And there are two goals of this preliminary study. First, we'd like to compare the performance between filter and the smoother for the parameter estimate. So we have three parameters in this model, A, B, C, and we know the true value. So we would like to perturb this value, assume this is the mean, and then we can randomly take some range and then create an ensemble and then try to compare how does the filter and the smoother compare in terms of estimating the parameters. The second goal is that we want to demonstrate the performance between a single grid and a two-grid multi-grid case. We have a number of numerical tests by varying the spatial grid size M and the assimilation frequency and how many time steps we would like to assimilate data. And then the in terms in the second term in the cost function. So how many time points in the big time window we have data available, and this is the example number. How many members we would like to do this assimilation? So,
sorry, Xinfeng, just you have 2 minutes to finish if you want questions.
Oh, okay. Okay, sorry about that. Let's. So I just show one case then, the solution profile. So this is the basically the compares what's the difference between MLF and MLS, so the filter and the smoother. And the red is smoother, the blue is the filter, and they are very close. The solution difference is really minimal. But what's the interesting part is that you can see the parameters A, B, C, and then you can see the MLS get closer to the true value. The true value is dashed line, and then they have quite a little bit in the very beginning, and then MLS give us a slightly faster convergence to the true value. So for the multi-grid or schedule this, come back to the multi-grid, one grid and two grid. And then as you can see here, MLS, here MLS means that only on the fine grid, fine resolution. The blue is two grid. And then they're very close, very close to the true value. But it will be really insightful to compare the computational cost at this solution error. But for these simple problems, and then the computational efficiency is minimal. And so it will be interesting in the future, a follow-up study, so we can get a more complicated problem, can demonstrate the computational cost. So move on to conclude the preliminary study. So we have we have some general idea how this parameters impact our solution between smoother and filter, and also this initial test of a two-grid multi-grid case is promising for parameter estimate. So future work will continue to improve this algorithm, and most importantly, and we'll implement this algorithm with XGRID, so can parallel in time as well. Thanks for listening, and then I'll take a question here.
Thank you, Xinfeng. I don't see any questions yet in the document, but Philip Brown has communicated a question to me. Philip Brown from ISDA-Online. He says that the multi-grid implementation with the smoother, is that similar to doing a 4D bar with different resolutions in either the inner or the outer loops, the different spatial resolutions in the different loops? Is that equivalent?
I think largely most feature equivalent, but the other part is that we want to do a parallel in time. So on the final mesh, on the final level, we can take we can do piecewise. We can take a window on a different. We do this parallelly. So that's the difference.
So the parallel in time is the extra thing that you're doing here.
Yes,
okay.
That's right.
All right, thank you very much for your talk. Let's move on to the next speaker.